So we've seen a number of different kinds of statistical technique, and what I want to do now is just talk through a few of the more philosophical differences between them, which are largely about the way in which different techniques deal with the unknown. I've talked about this big unknown before. So, crucial question that sort of underlies all of these statistical techniques is about what you know about the world. Traditional statistics says, I know nothing. Well, that's not quite true. It assumes you know, given what's true in the world, given your new system is better than the old one, how likely you are to see results. But it says, is system A better than system B? No idea. Is this coin biased or not? No idea. Assumes nothing, and then it tries to reason from that state of total unknowledge. Bayesian stats uses these prior probabilities. It says, you name the likelihood of these things. So instead of saying, I don't know, it says, put a number on it, put a probability on your system being better, put a probability on this being a fair coin or not, put a probability on whether my little die here is loaded. Put that probability on, take some measurements, and then I'll tell you stuff. So traditional statistics reasons from this state of unknowledge, of unknowing, whereas Bayesian statistics uses guesstimates and reasons from those. So different ways. In the end, there was a lack of knowledge, but they've approached it in a different way. The assumptions, right, are fundamentally different. So traditional knowledge, you have in traditional stats no knowledge of real values at all, no knowledge at all about the real world. So absolute knowledge. Bayesian, probabilities. So your assumptions start different, but however, in reality, they're not quite as different as it seems. So at one point, they seem philosophically worlds apart. One says, I'm going to preserve, and traditional statistics preserves that unknowledge right the way through, which is why you get those quite complex statements about what it means to be 5% significant, because it's never been solid about numbers. It doesn't say, you've got to tell me. It sort of leaves it to the end and says, I still don't really know. It could be that for some reason, I'll bet you this nice confidence interval. For some reason, it might be impossible that's in there at all. It's bound to be outside. But that's not, I'm not going to ask you to tell me about that to deliver this confidence interval. Bayesian stats says, give me the probability, I'll do it. They seem totally different. However, in reality, both have elements of the other. They're not as different as they seem. In traditional statistics, what you regard as an acceptable p-value depends on your beliefs about things, really. So if I had an experiment that appeared to be giving a really weird and unexpected answer, and I've got my nice 5% P, I'm going to probably ask for a bigger value. I'm going to want more from my stats. I'm going to look for a 0.1% p-value to really convince me. Now, I've not put a number on my probability, but I just have that feeling that, so just like in the Bayesian stats, I actually put a number on, said I am pretty sure that my system is better, or I'm pretty sure that it's not. In reality, you have those sort of feelings, and what you do is you adjust your bar as to what you regard as acceptable evidence in order to do it. So in physics, then there was, you might remember the neutrino experiment a few years ago when they thought they'd found a neutrino going faster than light. And that was based on quite complex measurements at multiple points, and they worked out their probabilities, and they had a number that was enough to feel they should publish it, but not enough to really convince people, because this was so against everything in science that you could have something faster than light. So they actually wasn't, even though it was actually for a HCI experiment, for the sort of things you do in usability, were being way outside the ranges we normally deal with in terms of what appeared to be its accuracy. In the end, people looked for more, and in fact it turned out not to be true. In Bayesian stats, the other's true. So Bayesian stats asks you to nail your colours on the mass. But in actual fact, people don't know. And that's why you get a lot of uniform distributions in Bayesian stats. You really don't know whether it's one thing or t'other. So you say, well, given my lack of knowledge, I have to put a number on. Bayesian forces me to put a number. I'll just make the number the same for everything. For unbounded distributions, you can't make it the same for everything because there's an infinite number of everythings. So what you do is you have distributions, and Cauchy is a classic one to use, which is a bit like the normal distribution, but with a bit more weight at the edges, at the tails. It's a little bit more spread out, sort of flattened, as a sort of fried egg. It's been flattened a bit. But still, as to be sort of uniformish, to sort of squish it out a bit and say, I'm not going to assume it's really tight towards the centre. So what Bayesians do is, if they don't know things, they choose a distribution that effectively assumes as little as possible by being as uniform as possible. Whereas traditional statisticians, when they do know something, they don't put it in as a number, as a Bayesian would, but they actually adjust their expectations. So although these two camps fight a little, and I said I will make recommendations about which ones to use, it's not quite as clear-cut as at first appears. Oh yes, I almost forgot, so I'm glad I've got my slides here. Ideally, in the Bayesian world, what you can do is what's called a sensitivity analysis. So you noticed when I gave my example, I put a prior up and then I showed a different prior, and we looked at the answers there. You can do that, you might try deliberately multiple priors, and that gives you some sense as to how much the knowledge you're putting into the prior has influenced what's come out at the end. For some reason, I'm not saying I'm saying massive amounts of this and it might be done, but I have not seen that done in Bayesian papers. It might be just the ones I've seen. It's certainly something to consider doing, and it gives you some idea of, in some sense, I was going to get it right. Yeah, as you've quantified your lack of knowledge, have you done that in a way that's really influenced the results?